bit late today because, as I was moaning, I'm just having issues. My life is falling apart sometimes. Well, it's not that bad actually, but sometimes I over-exaggerate and it feels like it. Last time we looked at how to take an R equals cosine theta, take away the sine of 2 theta. Remember those guys? And there's a bit of software. So I don't think I need to do that. You know, you're going to have a lot of fun, right? You know that we've got the software, it's already in Canvas, you can plug it in, but don't we get shapes? And I'm making this one up. I think the last one we got looked like a butterfly, right? And basically the kinds of questions you get are pretty straightforward. A lot of fun, but not going to take a lot of time. Don't you type that into the software and they give you 4 pictures. I don't know what the pictures are, you know, making them up here. And you pick the right picture and it's 1, 2, 3, or 4 and you're done, right? So nice, no frills, fun to play about with. I think so. So we are finished as far as everything you need to know for this week's homework and this week's test, right? So you're only going to be doing polar stuff, right? Polar coordinates and polar graphing. The graphing is going to be really quite easy. So focus on the polar coordinate stuff, right? Because that's where you're going to get most of your questions. We're now going to start a new section. I believe it's, well, I better check the number. I think it's chapter 9. I'm 90% sure it's chapter 9. And if it's not, I don't care. I'll tell you later. Let me just double check. It is. So 9-1 vectors in 2 dimensions. So a lot of notes today and some examples that I'll give. And then when you come back next week, we'll continue with this. So, a vector in 2 dimensions is basically you pick a point like P and you find another point called Q. And if you join P to Q and you go in that direction, that's called a vector, right? So a formal definition of what a vector is a directed line segment. P to Q in this case. Vectors are also called things like that. That is another way of describing this vector. You use a letter of the alphabet, typically U, V, and W, and we put a little arrow above it. When you look at vectors in textbooks, you have PQ, and they make the V bold. So when you look at web assign, the vector V will just be a bold. It'll look like the letter V, but it's a vector, and you know it's a vector because a variable is called V, but a vector is written as a bold V. Now, can you understand why we tend to write arrows above vectors? Because when you do it in paper, isn't it very hard to do bold? A lot of people don't know. Do you mean that? Do you mean just like X, Y, Z, or do you mean a vector V? You know, that kind of issue. So those are the 2 most common notations that you will see for a vector. Let's show you what are called the components of a vector. So if I say take the vector PQ, let's suppose I tell you the coordinates of P is 1, 3, and the coordinates of Q are 5, 9. Then the vector PQ is written with funny little brackets that look like this. And there's 2 numbers. There's a number going to go here called the X component, and a number that's going to go here called the Y component. And Imagine a little invisible triangle like this. The distance from here to here, how far along left or right you go, right? The X component goes here. So in this case, from there to there is 4. And the Y component is how far up you go. And from here to here, it is 6. So PQ would be 4 along and 6 up. Now there is a way or a formula for calculating the vector joining any 2 points P to Q. So let's suppose P was called x1, y1, and Q had coordinates x2, y2. Then the vector P to Q would be x2 take away x1, y2 take away y1. Notice that the 2 and the 1, notice the order. So if I did this example here, it would be 5, because that's basically x2, y2. This is x1, y1. So it'd be 5 take away 1, and it would be 9 take away 3. And can you see that I get the same answer as I did earlier? But having this formula, isn't it going to be easier than plotting them and counting boxes, especially if P and Q are like really ugly numbers or far away from each other? So for instance, suppose P was 1,75 and Q was 15,10, right? Do you really want to have to plot them on square paper and count how many boxes along and how many up and down you go, right? And maybe get the signs wrong. It's much easier just to use the formula. So the vector joining P to Q is x2 take away x1, y2 take away y1. In this case, it's 15 subtract 1 and 10 subtract 75. And I get the answer 14, negative 65. Okay, pause for a moment. Are you comfortable then that if I gave you the coordinates of a start point and where the end point is, that you could find the components of the vector PQ using this formula? Are you comfortable with that? And couldn't the numbers be as ugly as heck? Couldn't it be 17.9 3/4? And you could still do it if you had a calculator, right? Because it's second takeaway first, second takeaway first. So far, so good. So that's how you get the components of a vector, right, when you're told the coordinates P and Q. Let's talk about a very special vector called the zero vector. So today's really all notes. The zero vector is written like that. And the zero vector has components 0, 0. If I try to draw a sketch of the zero vector and I started anywhere I liked, wouldn't you just get a single dot? Because the vector would be start where you like and go 0 to the, in the X direction and go 0 in the Y direction. In other words, don't move. So the zero vector is a very special vector. It's the vector where there is no movement and the components are both 0. Let's suppose I have two vectors. Oh, let's look at two vectors, U, and it's going to have components 1, 3, and V is going to have components 5, 6, just for argument's sake. You can add vectors together. And some of you who've done, has any of you done vectors in other classes? Physics, mechanics, whatever? Are vectors totally new to you then? Right, you've not used them before. Right, you can add two vectors together. And since this is brand new to you, what do you think would be a sensible way to add these two vectors together?
x1 plus x2 and then y1 plus y2?
Yeah, just add the x's together and just add the y's together. In which case, what you've got 6, 9. Does that make sense that adding two vectors together is just adding their corresponding x and y components? That's nice. It'd be really horrible if it was some awkward thing. Well, if you wanted to subtract two vectors, there's u, subtract v. How do you think you would do that?
X2 minus x1.
Well, just subtract them, right? 1 take away 5, -4. 3 take away 6, -3. So I guess I should put it in here. 1 take away 5, 3 take away 6. So you just subtract the x and y components. You can multiply a vector. You can find the vector 2u, just like you can find 2x, right? Based on what's happened previously, what do you think you're going to do to find 2u?
Just multiply each x and y by 2?
Yeah. Intuitively, aren't vectors behaving the way they should? Right? They're not doing anything too weird, right? If you want to add them, you just add them, right? If you want to subtract them, just subtract them. If you want to double them, just double them, right? You can continue that process and do it with a combination. I could say, well, what about that? Well, that would be 3 times the vector u, take away 4 times the vector v. And I would say, well, okay, treble that guy, take away 4 times that guy. And then I'd say 3 take away 20 and 9 take away 24. And this gets me -17, and I believe this gets you -15. Does that intuitively make sense? That's how you, essentially that's the algebra vectors, right? How do you add, subtract, and multiply vectors and combine them in a way that makes sense? Any problems so far, or that seems reasonable? Let's try and show you visually then what some of those calculations I've done would be. Imagine I go u, 1 along and 3 up, right? 1 along and 3 up. That's the vector u. If you wanted to do the vector 2u, it would look like that. Isn't the vector 2u just the same direction, right? It's parallel to u. Isn't it just twice as long? Does that kind of make sense? That's visually what that would look like. Right? Now, if you take a vector u, which is this one, and you add the vector v, which is like this one. So you do the vector u, and then when u's finished, you add on top of it the vector v. That's what the red vector is, what u plus v looks like. It's a bit like, you know, doing a journey where there was a road and then another road. Isn't the adding the vectors just taking the shortcut, starting and finishing, and not worrying about taking the bend, right? So u add v is just a bit like the shortcut. U is the vector 1, 3. This is called the negative of u. What do you think negative u, what its components would be, what its numbers would be? Based on what's happened in all the other situations, what would you think this should be?
Just put a negative sign in front of each number.
Looks good to me, and it is. Now, if you try and draw that picture, imagine this is my vector u. If you draw this vector, it looks like that. You notice that they're parallel and that they're the same length. So what's the difference? Do you notice the difference is which way you point? Do you go up or do you come down? That makes sense? That's visually what a negative vector looks like. Writing it a bit weirdly, but what would you get if you took a vector u and you added its negative u? What would the answer be?
Wouldn't it be a 0 vector?
It would. That would be the equivalent of going this away and then coming back again. Wouldn't you end up where you started? Now, when you draw vectors, you do not start at the origin unless you want to. You can start anywhere you like. So according to the way we describe vectors, that guy could be u, and so could this guy be u, right? It doesn't care where you draw vectors. So vectors don't start at the origin. So let's not get into the habit of thinking that's what they do. They start anywhere. And secondly, that means, isn't there an infinite number of ways I could draw the vector u, right? There's 2 of them, but couldn't I draw them anywhere? So they have no fixed location. They start where you like. And so vectors are very often thought of as a movement, right? You start anywhere you like, and then you move somewhere. And you move somewhere according to this rule. 1 in the x direction and 3 in the y in this particular case. I think this is going okay, maybe because it's intuitive, it's obvious. Any issues? Okay. So we're just, you know, we've introduced this new thing and we're trying to find out all sorts of things to do with it. So let's find something else. We're going to find what is called the magnitude of a vector. Right, a magnitude of a vector is really another name for the length of a vector. So here's my vector I've been using a lot today, that one. Now, if I drew it, it would start somewhere. Wouldn't you go 1 box to the right, 1, 2, 3 boxes up, and there we go. There's my vector u. The length of that vector, right, is called its magnitude. The unit or the symbol that we use for it is a symbol that you've used for other reasons in mathematics. You ever seen that 2 vertical lines round something? Right. And you've probably seen it when you do things like the absolute value grade. Right. And when it's done in the context of a vector, it means the length of that vector, called its magnitude. Now, if you want to find the length of this vector, Would you agree I could do it with Pythagoras? 1 along, 3 up. And so according to Pythagoras then, won't the answer to the magnitude of this vector be the square root of 10? That makes sense? Let's generalize that to become a formula then. Suppose I've got a vector u and it's called x1, y1, right? Got to call it something. Then the magnitude of u is the square root of the components. Well, let's pick another vector. The vector v is 5, -12. If I ask you to find the magnitude of v, you're going to do the square root of 5 squared plus -12 squared, which is 5 plus 144. Sorry, 25 plus 144, which is 169, which is actually 13. Are we cool with that? We can get a magnitude of a vector. And the symbol that is typically used is 2 vertical lines that look like an absolute value symbol. That is not the only notation that you will see, but it is the only notation that you're going to see in WebAssign. Sometimes they do 2 vertical lines instead. So if you watch a video for someone else doing vectors and they write that down, they're talking about the magnitude of the vector v. If they write that down, they're also talking about the magnitude of a vector v, right? It's not anything different. It's just the notation. And you might read another textbook. I've changed my notation, but back in Scotland, we use that notation. I don't know if that's a European thing or not, but that I'm more familiar with. But I use that a lot now, so it comes second nature. So far, so good. So when I take over the world, we're going to abolish that symbol and use the double vertical line, right? But until that day, you keep using that one because that's what WebAssign uses. Okay. Are we so good? Let's move and talk about the I in j vectors. There are 3 vectors that are so special that they are represented separately. We've already seen the 0 vector. The I vector is this one, and the j vector is this one. So basically that is 1 in the x direction. And this would just be 1 in the y direction. Can you see why those 2 vectors are given their own letters, right? One's called the vector I and the other's called the vector j. Can you imagine that they might be special enough to get their own names? How are they used? Well, here's one of the ways they can be used. Forgot my usual, what's it called again? 1, 3, right? There's my vector that I like using a lot. Couldn't I represent this vector using that notation? When you write a vector down like this, it's ij notation. And when you write it like this, it's said to be in its component form. So some questions, the vectors are written like this, and other times the vector is written like that. So, for instance, here's a vector v. I could also write it down as 7i take away 2j. Would you agree that they're totally equivalent? They tell you the same stuff, right? Me personally, I like this notation better than that one. And I've just realized something that I haven't mentioned. Do you see the funny brackets I use look like greater than and less than symbols, don't they? They have got absolutely nothing to do with greater than or less than, right? It's just the brackets that we use, right? And when you are doing WebAssign, you will find a button that does that bracket. I'm not sure WebAssign will work if you do less than 7, -2 greater than, right? It might not work if you write the keyboard. If you go hunting for that one, I'm pretty sure it's under the vector submenu. You should be able to get that, okay? Now, it could be wrong. It could be that it'll take that symbol with the keyboard, but play safe with that one. So I could give you this question. And ask you to simplify it. The best way to look at this is collecting like terms and distributive properties. So let's see how it works. 3i plus 2j, distribute 8i, take away 4j, and then can't you collect like terms? 11i and -2j. Would you agree that adding, subtracting, and multiplying can be done just as well using this notation as it was with the early notation? And some people like I and j better than that notation. And I have no problems with whichever notation gels with your brain. Feel free to use it. I mean, they're totally equivalent, right? This guy is that guy is this, right? There's no difference. Does anybody like this one? Yeah, y'all like this one? You don't like either of them, Ali? I'm not asking Ali anymore. She depresses me. Grace, do you like either one of these?
I like the component form better.
Yeah.
I's and J's just look too much alike.
Which ones look too much alike?
Again, the I's and the J's.
They do, don't they?
Yeah.
I don't like them. I make mistakes at the best of times. Can you imagine how much more mistakes I can make if they look the same, or I'm careless when I write them down and I think it's a J when it's an I and then I add it? I shouldn't have. Yeah, I don't like it. So this is your choice. When you're doing your homework, even if the questions are written like that, you know you can just write them down like this to get the answer. Now, when you're putting it into WebAssign, yep, here's another little issue. You cannot write 11 keyboard I, take away 2 keyboard J. It won't allow it. You have to go into the vector menu and you will find one of those I's and one of those J's. So you actually have to use the buttons on the side. And I think I should actually do that right now and show you what I'm getting at. Let's see if I can get the vectors online just so I can show you what's what. Okay, that should allow me to do it. Okay. Right, I'm going to go into WebAssign and see if I can find our guy. I've lost the page. That's been my day to day. Okay, that'll do. Oh, darn it, I've lost it. I'll have to go in and out again. Third time lucky. There. This is the parametric stuff, but that's fine. I just want it so I can press a button somewhere. Let me press a button, come on. Okay, that was a bad choice. Let's try it this time. As I say, this has been my day today. Nothing quite goes as smooth as I want it. Right, are you looking at polar coordinates 8-1? Yeah. Okay. Just so I can put a box somewhere. Okay. Let's say box. If you go over to the vectors, click on it. There's the I and the j I'm talking about. So let's suppose your answer was 2i plus 3j, right? You go 2i plus 3j. You see, that's how you have to type it in. If you type in 2 keyboard I plus 3 keyboard j, would you agree at least superficially it looks the same answer, doesn't it? But the Weber sign will just say you're wrong. So you got to live with that. Second guy is, do you see those little brackets I'm talking about? The ones that look like that? That should do it, I hope. I think if I just click out, it'll take it. There it does. Do you see the funny little brackets I've been talking about? That's where they live, right? So
what's the bold button for?
What bold button? These guys?
Go back into the vectors thing. I think it's like the first button. Yeah.
Oh, can you imagine you've got a vector called A, B, C, D, and E? Then if you hit the bold button, well, I better clear this out of the way. I should be able to do A. I don't know if I need to highlight it. I'll highlight it and I'll hit the bold button. It's now the vector A. So if your answer was the vector A plus B, can you imagine that was your answer? It was just two vectors added, one called A and the other B. Then you would do A plus B, and there's your vector in bold. Actually, I've never seen that before. Oh, there is the little arrow guy. Can you remember PQ? That's how you would do PQ. If your answer happened to be PQ, that's how you would write it. So in the vector submenu, that's the guys that you're going to be using quite a lot in this group of questions. Any other questions about this before we go back to doing some more notes? Cool. Right. So, just so you don't get that frustrated thing where you do the right answer and then WebAssign says you're wrong because it wasn't a bold I, right? That kind of thing. Hopefully I've caught that before it gets too bad. Next fella we're going to look at is called a unit vector. Imagine I've got a vector u. It's 3, -4, right? So if I draw the vector u, it probably looks something like this. There, that's vector u. A unit vector is a vector parallel to u but whose length is 1. So if I was trying to say what does a unit vector look like, that guy there would be my unit vector. You see him? Parallel but 1 unit long. Right. So there must be a way in which we can find the unit vector of any vector. Right? So first thing I'm going to do is find the length of vector u, its magnitude. It's 3 squared plus -4 squared. And that is 9 plus 16. Square root of 25, it's 5. So that's good that I get a nice number. The unit vector what do you think I do with that guy? to make it into a vector that is 1 unit long? Because right now this guy is 5 units long. So how would I make it 1 unit long?
Divide by 5.
Divide by 5, and we will call that 1/5. So your answer will be 3/5 negative 4/5, and that's the unit vector. Are you comfortable about how we calculate the unit vector? You find the length, the magnitude of the original, and then essentially divide by that number. And the way we write down divide is 1/5, for example. Let's have a vector A, and it's going to be 1, 2. Let's find its unit vector. The magnitude of A is the square root of 5. The unit vector is going to be 1 square root of 5, this vector, which is going to be called 1 over root 5, 2 over root 5. Are we good with that?
Do we leave it with the
Square
thing
root
on the
of
bottom?
them?
Yeah.
No. WebAssign might, but it's a good habit not to. So I'm going to rationalize the denominator. And I'll cut out the middleman, but hopefully you could say, yeah, that's what I would have got. Right, agreed? Right, so I want to try and write that as a formula. So here we go. The unit vector, let's call it U, right? U for a unit vector of any vector A is this guy. 1 over the magnitude of A times A, great? And that's essentially what we did. So we now have a little formula for doing it. Any questions? Are we happy about unit vectors now? Let's do, I don't know what to call this. Call them journeys. So good a name as any. Sometimes you get vectors. Oops. Yeah, that's better. That's what I'm looking for. That's much better. Okay. And in this case, we've got P, Q, R, S. Okay. And you get vector addition written down, or journeys, like this. What single vector would be the same as PQ plus QR? So you go from PEQ, and then you go from Q to R. What single vector would do the same job?
PR?
Great. Would you agree? You start P, you go Q, you go R. Isn't the single, take the shortcut, isn't it P to R? But this one. PQ, QR, RS, SQ. Yeah, that's a bit of a challenge. But if you notice a pattern, you should be able to tell the answer very easily. What single journey, what single vector? Can you tell, hopefully you've seen a shortcut, can you tell how the easy way of doing one of these long-winded 4 or 5 step journeys. Can I just see what's going on?
What I noticed was it's the first point and then the very last point.
Right.
Is that
Yeah.
not true?
It is true. As long as they're matching. Do you see how they match? They match. In other words, where you left is where you start the next journey, right? Where you finished is where you start the next journey. And if that's the case, then the only guys that really matter is where you start and where you finish. Agreed?
And could this be written as QP too? Does that make any difference?
It does make a little bit of difference because QP is you going from Q to P and not P to Q. So it's the same start and finish, but the order, i.e. the direction you do it, is part of the vector. So a vector isn't just P to Q or Q to P, it's got a direction to it as well. You're going from P to Q. If you wanted to do Q to P, although it would look very similar, wouldn't the difference be that? And so in this case, you started at P and you finished at Q. That's why it has to be written that way. What would this one be? And it's a bit of a trick question. I did warn you, it's a bit of a trick question.
It would be a zero vector.
Oh, I got a 0 vector right off the bat. Well done. What was the other answer going to be? It may have been 0 as well.
Oh, I said 0. I think he did too.
Yeah, so it's a draw there. You could have said P to P, but isn't that 0 vector? Because you never went anywhere, technically, at least. Are we good? Side issue. Right. Then I'm going to give you some questions to try out and see how you go. So U is going to be the vector 1, 3. V is going to be the vector -1, 2. And the third and final vector W is going to be 5, 3. And here are your questions. First one is just a calculation using all 3 vectors. Second one is a subtraction. Third one is a magnitude. The fourth one is a magnitude as well, but a little bit more complicated. And the fifth one is a unit vector question. Last question. Okay. So I'll just 5 minutes. Who knows? I may be a little bit more. I may give you a little bit less. 1 minute each question. That seems reasonable. Got it out. Come on. Yeah. Well, there we go. Yeah. Oh, no biting. No, no biting. Yeah, kisses. Okay. You go down there and behave. Okay, last few moments. Okay, so essentially what we've been doing today is introducing you to vectors and for the most part, doing the algebra of vectors, which is how do you calculate with them. So 2 of this guy, 3 of this guy, plus 3 of this guy. So that gets me 2, 6, -3, 6, and 15, 9. And then you do 2 and that, and I believe that gets you 14. And then you do 6, and 6 is 12, and then 9 more is 21. Did I do that one okay, guys? You agree on the first one? 14, 21? Can't see any nods. Did I make a mistake? Tell me now. Okay. Assuming nothing is wrong. 5 times this guy gets you 5 and 15. Take away 2 times this guy gets you 2 and 6. 5 take away 10 is -5, and 15 take away 6, I believe, is 9. Have we good on that one? Right, getting nods. This one is basically just straight out of the question. You're going to take u, which is this guy, and you're going to take 1 squared plus 3 squared. So the answer is just the square root of 10. So that's pretty much the end of that. Watch out for Weber sign. Square root of 10 is fine. Yeah, I don't see anything you could do to fix that. But can you imagine that you might get the square root of 20? That can happen. In which case you have to realize that it can simplify. So just in case Weber sign was expecting that and you type in that. So just be on the lookout. Right, this guy, you don't actually need to do it, isn't it? This guy, right? So I'm just using this answer and finding its magnitude. So it's going to be -5 squared plus 9 squared. So it's 25 add 81, and I believe that's 106. How's that one look? Square root of 106, does that look good? I'm not sure if that's a good or a bad sign. Nobody's saying no, so let's assume it's right. And final question.
Not something different, but I don't know.
It could be me. Did you have these numbers? Did you get this for 5u take away 2w?
Yeah.
And 5 squared is 25. Yeah. And 9 squared is 81. Yeah, 106 looks good to me then. Right. Last one, unit vector. Well, I'll find the magnitude of vector v, which is this one here. So it's going to be the square root of -1 squared plus 2 squared. Actually, whenever you square something, you're kind of guaranteed to get a positive number. So you get square root of 5 in this case. And so our unit vector is, I'll call it you. I can't call it you, somebody else is called you. Is 1 over the magnitude of the vector v. So it's going to be 1 over root 5 times that guy. And that gets me -1 over root 5, 2 over root 5. And if you had time, you could convert that into negative the square root of 5 over 5 and 2 root 5 over 5. And I think that's a good place to finish today. So your homework will not include any of the vector stuff for today. That will be the following weeks. But your test is going to be on all the polar stuff, chapters 8.1 and 8.2. And that's it. So make sure you put your attendance and bye-bye, and I'll hang about for any questions at the end.
Thank you.